We now spend a little time looking at cell aging from a qualitative point of view, not a quantitative. We're not here seeking to make models of degradation mathematically that describe how it happens, to be able to predict it in that kind of sense. Here we are more concerned with just having some idea, without all of this just kind of bland discussion, hand-waving discussion of, oh, it's side reactions that's happening. I'd like to go a little bit more deeply than that into this. This is based primarily on this paper cited on the bottom of the page by Vetter and some colleagues. That is a survey paper that brings together a lot of information from a lot of places to kind of summarize what was known at that point in time about how lithium-ion cells age. And from a qualitative point of view, I don't think much has changed since that paper was published. Quantitatively, there have been some advances in modeling the degradation, although there's surprisingly little modeling of degradation available, actually. So we're looking at qualitative, just the answering the why question. Why do cells degrade? We're going to look in this section at degradation that occurs within the negative electrode, and then the next section we'll look at the positive electrode, and there are similarities and there are differences. And in the negative electrode, we have aging at 3 different scales. So if we look at the electrode itself, we know there's a bunch of particles in the electrode. The first location of aging is on the surface of the electrode particles. We'll look at some things that happen there first. And then within the particles themselves, we'll think about that. And then within the entire structure of the electrode, we'll look at aging there as well. So first, the surface. We are going to assume in this section that the active material in the negative electrode is some kind of a graphite-like carbon, possibly coke even, or hard carbon, but some kind of a carbon that generically has the C6 chemical formulation. There are different kinds of negative electrode materials. Carbon is used in practically every commercial cell at this point in time, but there are some competing electrode chemistries. One of them that's getting a lot of attention in research is based on silicon. It's in the periodic table, it's in the same column, it's a different row, so it has some similar properties, but it's actually fairly different. Silicon has a lot of ability. It can store more lithium per silicon atom than carbon can per carbon atom, so that appears to be an advantage of using silicon in a negative electrode. However, there are vastly different aging properties of silicon that have not been solved yet, and so silicon is not being used in any commercial product that I'm aware of because it ages very quickly. Another possibility for a negative electrode is lithium titanate oxide. Lithium titanate oxide has the disadvantage that it's a fairly high voltage material. It's about 1.5 volts, whereas carbon is about 0.1 volts. And remember that cell voltage is equal to positive electrode voltage minus negative electrode voltage. So I want to have a very small negative electrode voltage in order to get a big cell voltage and therefore more energy in my cell. So that's why people use carbon, plus it's inexpensive. However, so this lithium titanate oxide has this higher voltage, which means that its ability to store energy, its energy density, or specific energy, is quite a bit lower than the carbon-based negative electrodes. But it does not degrade nearly as quickly. Lithium titanate oxide can be used for very high power applications, and it's practically indestructible. You can charge and discharge an LTO battery forever, and you will see very little aging. So we're not talking in this section about LTO. excuse me, we're not talking about silicon in this section. We're really focusing on carbon because that's what's used now and it's what's likely to dominate for the foreseeable future. But there are alternatives on the horizon that will be used at least in specialized applications, and maybe they'll even take over eventually. That remains to be seen. The graphite negative electrode operates at cell voltages that are very low, and these low voltages are outside the comfortable window for electrolyte components. Technically the electrolyte, the solvent, is unstable at these voltages, and the solvent just wants to break down, and it wants to chemically react with the carbon. So in other words, the electrolyte wants to decompose. That's why it's unstable. It wants to form other compounds with the graphite, the carbon from the graphite. So what happens is when a molecule of the solvent comes into contact with the carbon, there's a chemical reaction, a reduction, and the process consumes lithium. So when this chemical reaction happens, it's a little bit of the electrolyte solvent plus some lithium plus some carbon forms something else, and usually the first product that's formed is lithium carbonate, IUM carbonate. That takes the ethylene carbonate from the solvent and lithium from something else and adds some carbon from the graphite. This process turns out to happen mostly, not entirely, but mostly at the beginning of the cell's life, especially during what we call the formation cycle, the first time we charge a battery cell. When we construct a battery cell, the negative electrode is pure carbon, no lithium in it at all, and the positive electrode is fully lithiated. We have it completely full, beyond its operating capacity, its total capacity of lithium. And when we charge a battery cell for the first time, we call that the formation cycle, and we're moving lithium from the positive electrode to the negative electrode. And at that point, when we introduce lithium into the negative electrode, we have all of the components necessary to make this lithium carbonate. We have lithium, we have the solvent, we have the negative electrode material, and a reaction happens. And this reaction produces something called a solid electrolyte interphase. This is spelled correctly. Sometimes you will see interface, thinking about where two materials come together. That is, I think, also accepted in the literature, but the most careful chemists and material scientists, when they're publishing, will use the term interphase because it's talking about the solid being a phase and the electrolyte being a phase, and this SEI is forming at the boundary between the solid phase and the electrolyte phase, so it's an interphase phenomena. The picture here is showing an image, and I don't remember the technology that was, I think it's FIB, focused ion beam technology, that was used to create this image where they sliced an electrode particle in half so you could see a cross section. And if your image quality is okay, you'll notice that there's that is the interior of the particle here, and then on the surface of a particle we have this layer that was formed, and this layer here is the SEI, the solid electrolyte interphase. And in this picture, that's about a 10 nanometer thickness. Now, the layer that's formed has the property that it greatly inhibits the ability for more SEI to form. if that layer was not there, the electrolyte out here, the solvent in the electrolyte would want to react with the carbon, and it does so very quickly, very violently. Not that you see the violence, but it happens very quickly, and it forms that layer. And once that layer is there, it's kind of an insulation, and it keeps the ethylene carbonate away from the carbon surface layer, or it tends to keep it away. And so the reaction slows down, and the formation of this SEI layer slows down. So that's why we say the process occurs mainly at the beginning of cycling, because once we have this surface film, it almost stops, but it doesn't completely stop the formation of SEI, and we'll talk about some reasons for why that is. But it greatly slows down the formation of SEI after that first cycle. So if you look at some authors who aren't really concerned with tracking aging, they may even say that SEI forms only during formation, but that's not true. It really does continue to form, and it has been observed to do so. And but if your focus is not on aging, that might not be your concern. Okay, so SEI is a passivating layer. It covers the surface of the carbon in such a way that it tends to slow down the chemical reaction that forms SEI a lot. Lithium is consumed as part of the SEI formation. That's why the capacity of the cell goes down. I don't have as much lithium to go back and forth. The SEI film is not a solid wall. It has pores in it, and the pores are small enough that lithium can still go into and out of the carbon particle. So lithium can go through the SEI layer, but it is harder for lithium to go through the SEI layer. So the resistance to ion transfer of lithium through this layer goes up, and so the resistance of the cell goes up. So capacity is going to go down, resistance is going to go up. And the porosity of this film is such that the pores are small enough that lithium can still get through, but the solvent really cannot get through well. So that's why it slows down the reaction with the solvent. It does pretty much form a barrier for the solvent, not completely, but at least to a great extent, for solvent to get through, but not lithium. There's a lot of papers where people are evaluating what is SEI, and they usually do so by aging cells and then using specialized equipment to probe this SEI and finding the content of certain elements inside of it. It appears that SEI is not a uniform composition. On the previous page it was called amorphous. It's not a crystal structure where it has a regular construction. Instead, it's somewhat random, and it's probably not uniform. It seems that there's evidence that first there's some initial products that form, and then those products are not terribly stable themselves, and they tend to deteriorate, so they decompose, and then more stable products are formed. So it's like A goes to B goes to C, kind of a process. And it's thought that the SEI film near the surface of a particle has a different composition than the film at the exterior, right at the electrolyte interface, that there are layers actually, but amorphous layers, not structured layers in the SEI film. So that's interesting. It's a great modeling challenge. You have to understand what's there first and then how to model it. That's not our focus here though. When we're looking at continued aging beyond the first cycle, SEI is still growing a little bit because the solvent can still enter in through this porous structure, but there are things that tend to accelerate the growth of more SEI. One of them is high temperatures. High temperatures cause chemical reactions to happen more quickly, and if there is a decomposition reaction that's happening anyway, that's just going to happen faster. And so that can break down the SEI layer and actually leave holes in the SEI layer where more graphite is exposed. The SEI just disappears and there's graphite exposed. Oh, and then the solvent immediately reacts with the graphite and causes more SEI to form at that point. Again, lithium is lost, resistance increases. The bigger effect there would be loss of lithium than increase in resistance, because when I broke down the SEI, I did not gain capacity back, but I did gain less resistance back. But when I reform, the resistance again stabilizes and the capacity goes down even more. So high temperatures can cause an accelerated aging. Pores in the SEI holes still do allow solvent to penetrate, as we've said, and reach the surface, and that allows more SEI film to grow. We insert electrolyte into the cell when we're constructing it in a dry environment so that there's not very much water. However, there's always some amount of moisture in the air when you're forming the electrodes to begin with and so forth. So there's going to be some trace water. We don't want there to be much, but there's going to be some trace water in the electrolyte. And trace water is a problem because I've got usually something like LiPF6 is my salt in the electrolyte, and that breaks down, as you know, into Li plus and PF6 minus. However, in the presence of water, this PF6 minus is not stable, and it breaks down further and forms hydrofluoric acid. And hydrofluoric acid is really nasty stuff. It's very, very harmful to human beings, so there's not going to be enough in the cell to leak out and probably injure anyone, but there is any amount of this hydrofluoric acid can cause deterioration of the components of the cell. And one place where it does so is by attacking and decomposing the SEI layer. And as the SEI layer breaks down because of this acid, it exposes more graphite and more SEI forms. Capacity goes down again. We're going to talk also about how the positive electrode ages, but some kinds of positive electrode aging result in deterioration of the material. And so, for example, in an LMO material, lithium manganese oxide, we could have manganese ending up in the electrolyte, and manganese is small enough to go through the separator and to land on the negative electrode particles, and they can be part of the SEI. And we call this anode poisoning when this happens, the cathode breaking down and forming materials on the anode or the negative electrode. It happens with other materials, not just manganese, but manganese is one that a lot of people have studied. When this SEI layer is not electrically conductive, it can cause an increased resistance. And when we have these materials, so like Mn2 plus manganese from the positive electrode coming in, it tries to intercalate into the negative electrode, just like lithium does. You know, you've got lithium plus, they're both positive ions, and they both want to intercalate into the graphite when we're charging a cell, except the manganese is physically a much larger atom and it doesn't fit. So it can plug the pores, and it can make products where it's permanently plugging a pore. And by a pore, I'm thinking of not pores in the electrode structure, but I've got layers of graphite, and I could have a manganese plugging that entrance there, and I can't get lithium into or out of the structure anymore. Those blue dots can't come out that way. Maybe they could go out a different way, but once that entire layer is blocked off, I've lost capacity. We've looked at high temperatures. There's also things that happen at low temperatures. At very low temperatures, diffusion in the particles is slower. And as charging is forced, if I'm looking at a particle, I'm forcing lithium into the particle. And if the surface layer is completely full of lithium, I can't put any more lithium. Well, all I know is I've got an Li plus here, and I've got an electron E minus somewhere else, and it's trying to combine. And if it can combine any other way, and I'm forcing it, it will still appear that I'm charging this cell, but in fact I'm not, because lithium is not going into the particle, it's doing something else. One thing that can happen is that the Li plus and the E minus becomes atomic lithium, metallic lithium, on the surface of the particle rather than going into the particle, and that's called lithium plating. And lithium plating, once I become lithium metal as opposed to lithium ion, I never get that lithium back. Doesn't necessarily stay metal. It might, or it might then further react to become lithium carbonate and form part of the SEI. But once I lithium plate, I never get it back. Lithium plating is something that we hope would never happen, because we have to be pushing the cell, charging the cell really aggressively at cold temperature. Or I guess even more aggressively at warm temperature, you could still do it. This is why we have voltage limits on a cell, as we will discuss in a later chapter on power estimation, is if we obey certain voltage limits, we should never lithium plate. We still might, but we should never lithium plate. But if we disobey the voltage limits, we can plate all day long. Well, no, we can't. We can plate until there's no more lithium left, and that happens really quickly. I've had some lab results where we have forced charging of a cell, and within 2 cycles this lithium ion cell was completely gone. There was nothing left. So we forced it at cold temperature. So don't charge your cells at cold temperature too quickly. When you do lithium plating, it makes it more likely that you're going to lithium plate in the future. Once you've got metallic lithium, it's easy to grow more metallic lithium on top of it. And metallic lithium forms really interesting looking structures. And this here is what we call lithium dendrites. They look almost like snowflakes. So we have these metal things, and they can pierce the separator and cause a direct short circuit between positive and negative electrode, which of course makes the cell not be able to hold charge any longer. And it can lead to, because of the high currents that flow in the short circuit, it can lead to overheating and even fire. So this is really bad news. We don't want lithium plating to happen. Here's a picture from the Vetter paper that tries to summarize the surface effects of that we've talked about. So we have the particle made up of graphite, which is itself composed of layers of graphene. We have solvent. Those are these funny looking things. When they come against the graphite, they will form this SEI product, and it loses lithium in the process. We can generate gas as part of this, by the way, and that can cause your cells to bulge, and it can even cause your cells to vent, meaning that they open up and you vent gas to the environment. And some of the gases that are formed include hydrogen gas, so there's a potential safety hazard there if there's enough hydrogen gas that's developed. So we form the SEI layer, and over time there's a stabilization of this layer. The first cycle, we said, was where we lose most of our capacity, but there's still some possibility for more SEI growth. And then we said that because of acid attack and high temperatures and so forth, the SEI could dissolve, and then we could have it precipitate in the bottom of the cell, or it could just plug out the pores of the cell and so forth. And because we've dissolved SEI, there's opportunity for making more SEI. And we also mentioned that there could be interactions between positive and negative electrodes, such as you see this Mn2 plus here that could come in and block some pores, and that would lose capacity. And then we also said there could be lithium plating if we try to charge too quickly, and then the other reactions that happen after the lithium plating when the lithium metal tends to react and form more SEI in different products and so forth when it reacts with its environment. So those are the surface effects. We said there's three places aging occurs. One is surface, one is in the particles themselves, and the other is in the electrode. So let's look at the second one, which is negative electrode aging in the particles themselves. When we charge and discharge this cell, we are putting lithium into something that didn't previously have lithium in it. So if you think about putting water in a sponge, whenever you do that, the sponge expands because there's water in it. And the same thing happens when you put lithium into graphite. It expands. Anisotropic, so it doesn't expand the same way in every direction. In some directions it expands more than in other directions. Now the volume change is relatively small. It's less than 10%. 9% is a number that I've seen quoted. But that's still enough to cause some stress in the particles when lithium is inserted and deinserted. And that can lead to cracking. So we have a picture here of a particle that you can definitely see there's cracks in this particle. You say, whoa, that probably didn't start that way. But over time, it developed a crack. When I have this crack, that opens up more surface, and SEI can form on the exposed graphite, so I, again, lose capacity and increase resistance. If I have layers of graphene making graphite, and I have solvent intercalating, that can force the outer layer to flake off, called exfoliation. And that means that there's no longer this outer layer. Now, this here is just a floating piece of graphene. It can't store lithium by itself. I have to store between layers. So this is now my outer layer. And then over time I could flake more and more and more off. So why does it flake? I don't know if I said so, but if solvent gets in, solvent is a large molecule compared to lithium, and so that causes pressures in here that just tends to make the layer break off. Also, if the solvent, when the solvent reacts with the graphite, if it reacts inside the particles, it can accelerate cracking. Now, I've shown this beautiful graphite layers that are all perfectly lined up, but you might remember from last semester that we said, well, it's a little bit more complicated than that, because most of these carbons have, there's one particle, and there's kind of large voids inside, or possibly large voids inside, where this solvent may intercalate to this large void and react inside there, causing gas inside of that particle to tend to accelerate and crack and so forth. So it's not quite as pretty as this, where I've just got pure layers of graphene together. If I did, these aging mechanisms would not be able to happen quite so well. Third place that we can have aging in the negative electrode is within the entire electrode structure itself. So there's stresses and strains that caused by intercalation and deintercalation, and maybe even external pressure on the cell, that cause mechanical and electronic contact loss. So if I've got particles that are jammed together, and there's stresses and strains, over time those particles may not be jammed together anymore, and where I had electron conductivity, I no longer have electron conductivity because those particles are no longer joined. And it's believed that a certain amount of these particles actually lose contact, electrical contact with anything, and they're just kind of floating in space. And once I'm floating in space, that capacity, while it's still there, can't be accessed because I can't get an electron to it any longer. So between particles, between current collector and particles. So the current collector is this sheet of some kind of a foil, usually a copper foil, and I start out with the particles adhered to it, but anytime you've got two dissimilar things that you're supposed to have in contact, well, they may delaminate, and so I may have particles that have lost contact with the current collector, and maybe there's some electronic path still, so I don't lose the capacity, but I have a greater resistance because this former electronic contact is now gone, and it's harder to get an electron to where I want to be. So I may lose capacity because I completely disconnect from the matrix of particles, or I just may gain resistance because there's not the simple electronic path that I started with. Now we have, remember, in the electrode we've got the active particles, we have the electrolyte, but we also have stuff called binder. And binder is some kind of, usually a rubber, PVDF is one of them that's used, that tries to add some elasticity and to keep the particles in contact with each other. But the binder over time may age and stress and react and degrade and so forth. So this can still happen. And of course the binder in the current collector also can cause delamination. So certainly this would result in higher impedance because there's fewer paths for electrons to follow, and it can result in capacity loss if the particles are completely disconnected from current collector and each other. The porosity of the electrode, epsilon E, that's where the electrolyte is, the volume fraction of the electrolyte, that can be reduced by volume changes and growth of the SEI. So we're consuming some of the electrolyte chemical stuff, the solvent, and forming this SEI product, which is jamming the holes in between the particles, and that's making it harder for lithium ions to move in the electrolyte, and so that's going to increase resistance. And another thing that could happen is if I over discharge a battery cell, I can achieve low voltages of this cell, which turns out to be a high voltage of the negative electrode, near about 1.5 volts at the cell level, where the copper current collector can corrode. Means that it reacts with its environment, it reacts with the electrolyte, and that releases Cu2+, copper ions, into the electrolyte. So there are some impacts. One of them is a reduced contact between the current collector and the particles that leads to higher resistance. By the way, this is a picture of a corroded copper, and you can see the pitting in there. This was from a cell that was purposely over discharged so that they could then take the cell apart and look at the copper and see what it looked like. And you can see it's a fairly large scale, 1 millimeter on that picture, and you can definitely see holes in there. The corrosion products, if copper forms products with the electrolyte solvent and so forth, it makes basically more SEI, and it gives a higher resistance. It can lead to non-homogeneous current and potential distributions. So we have accelerated aging in certain parts of the cell versus others because they tend to react more and heat up more, and that would also give a preference towards lithium plating. And copper itself, just like we said with manganese, if manganese dissolves from the positive electrode, copper is a positive ion, and it tends to want to cycle just like lithium does when you charge and discharge a cell, and it's small enough to go through the separator. It can go from the positive electrode area to the negative electrode area. And when I'm charging, it's going to try to go into a negative electrode particle, but it's too big to do it. So it can either block a pore and basically plate metallically on the surface of a particle. And once you've got anything metallic, it tends to allow other metallic things to grow more quickly. So if I've got metallic lithium, or metallic copper or metallic manganese, any of those would tend to accelerate lithium plating or dendrite growth or anything like that and cause short circuits. So if you over discharge a battery cell, especially if it's a forced over discharge rather than a very, very slow self-discharge, a self-discharge you can sometimes recover and be okay. But if you are really pulling current out of the cell and you have this copper dissolution, the current collector corrosion, it tends to cause short circuits, soft shorts usually, where there's just this metallic bridge that's formed between the negative and positive electrodes that's always conducting some current, and you can never keep a cell charged after that point. It's like the bucket has a hole in it. You can't. There's always a leak of charge, and once you have that happen, the cell is pretty much gone. Some people say if you shock the cell with a very high voltage, very short pulse, you can burn these bridges. It sounds like it might happen, but I don't believe it is guaranteed to happen, and would certainly not recommend doing that. This table summarizes what we've talked about as some of the aging mechanisms, probably the primary aging mechanisms in negative electrodes, and I've copied this or reproduced this figure from Vetter's paper, and those that are in boldface are the ones that people think are probably the prevalent mechanisms for causing capacity fade and power fade. And I'll let you read through that. I won't dictate this table for you, but I hope that this section has given you a better appreciation for why aging happens in the negative electrode of a cell. And now we'll look at the positive electrode.